Ethereum 3.0, scaling to 10,000 TPS through hardware acceleration. Ethereum, since its inception, has been a groundbreaking decentralized platform enabling the creation of decentralized applications, dApps, smart contracts, and decentralized finance, DeFi. However, one of the primary limitations that has consistently hindered Ethereum's scalability is its transaction throughput. Ethereum's current Layer 1, L1, can handle only about 15 to 30 transactions per second, TPS, which, while sufficient for a smaller user base, has become a bottleneck as the platform continues to grow. As Ethereum aims to expand its global user base and support complex applications such as DeFi, NFTs, and potentially even AI computations, scaling to higher TPS is no longer optional. With the rise of competing blockchain networks like Solana, which boasts a theoretical 65,000 TPS, and the increasing adoption of Layer 2 solutions, Ethereum must find a way to improve its scalability without compromising its decentralization and security. The proposed solution to Ethereum's scalability problem lies in hardware acceleration, a transformative strategy that could elevate Ethereum from its current capabilities to a new frontier, 10,000 TPS. In this exposition, we'll explore how this hardware approach can unlock Ethereum 3.0 and ensure its position as a leader in the next generation of decentralized networks. 2. The role of hardware acceleration. To fully grasp the significance of hardware acceleration, it's essential to first understand what it entails and how it differs from traditional software-based solutions. Hardware acceleration refers to offloading computational tasks that are normally handled by the CPU to more specialized hardware components, such as graphics processing units, GPUs, tensor processing units, TPUs, or even application-specific integrated circuits, ASICs. These specialized processors are optimized to perform specific types of operations much faster and more efficiently than general-purpose processors. For Ethereum, this could mean using hardware designed to process transactions and validate blocks in parallel, rather than sequentially. Here's how hardware acceleration can significantly boost Ethereum's scalability. Parallel execution. Ethereum's current system executes transactions sequentially, meaning each transaction has to wait for the previous one to be processed. By leveraging hardware accelerators like GPUs or TPUs, Ethereum could execute many transactions simultaneously, vastly increasing the TPS. Optimize cryptographic functions. Many of the cryptographic functions used in Ethereum, such as elliptic curve digital signature algorithm, ECDSA, or verifiable random functions, VRFs, could be significantly sped up by specialized hardware, further enhancing the blockchain's overall throughput. Improved consensus. Integrating hardware accelerators into Ethereum's consensus mechanism, proof of stake or POS, could also reduce the time needed for block validation, potentially allowing the network to process transactions more quickly and with greater energy efficiency. In comparison to Solana, which uses parallel processing to maximize throughput, Ethereum's existing architecture is limited by the fact that it must process each transaction individually. Hardware acceleration would allow Ethereum to transition from its current bottleneck to a level where it could compete with other high-performance blockchains. 3. How Ethereum can achieve 10,000 TPS. Achieving 10,000 TPS on Ethereum is an ambitious but feasible goal with the right hardware optimizations. The process can be broken down into several key components. A. Transitioning to parallel transaction execution. Ethereum's current architecture relies on single-threaded execution, meaning each transaction must be processed in order. However, with hardware acceleration, Ethereum could implement parallel transaction execution similar to Solana's C-level engine. This would involve partitioning the network's data and processing multiple transactions at once, rather than sequentially. By using GPUs and TPUs to handle large batches of transactions simultaneously, Ethereum could significantly increase its throughput. The integration of hardware accelerators could unlock a new form of transaction processing, where the network can handle hundreds or even thousands of transactions in parallel, increasing TPS while reducing bottlenecks. B. Transaction batching and compression. Another key area where hardware acceleration can help Ethereum scale is in transaction batching. By grouping multiple transactions together into a single bundle, Ethereum can reduce the computational cost of processing each individual transaction. Furthermore, compression techniques could be used to minimize the amount of data that needs to be transmitted and stored across the network. Hardware acceleration could speed up these processes, making transaction batching and compression more efficient. C. Optimizing proof-of-stake validation. Ethereum 2.0's transition to proof-of-stake, POS, already lays the groundwork for scalability by reducing the energy consumption associated with traditional proof-of-work, POW, systems. However, further optimization of the POS consensus layer could benefit from hardware acceleration. Specialized hardware could improve validator node performance, allowing for faster block finalization and quicker consensus confirmation. In essence, hardware acceleration will not only increase transaction throughput, but also reduce latency and enhance overall network efficiency, making 10,000 TPS a realistic target. This content is brought to you by Bobby Gigs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. 4. Potential hardware solutions for Ethereum. In order to reach the ambitious goal of 10,000 TPS, Ethereum would need to adopt cutting-edge hardware solutions. Some of the most promising hardware options for accelerating Ethereum's Layer 1 are as follows. A. Graphics processing units, GPUs. GPUs have long been used in blockchain networks for mining, particularly in networks like Ethereum before its transition to proof-of-stake. GPUs are well suited for parallel processing tasks due to their architecture, which allows them to handle many operations simultaneously. For Ethereum, this means that GPUs could accelerate the execution of transactions, cryptographic functions, and even consensus mechanisms. While GPUs are currently used in Ethereum's mining process, their potential in transaction validation and block propagation is still largely untapped. Ethereum could integrate GPUs into its architecture, allowing nodes to process transactions in parallel, significantly reducing transaction times. B. Tensor processing units, TPUs. TPUs are specialized hardware designed specifically for machine learning workloads. While Ethereum doesn't currently leverage machine learning in its operations, the general computational advantages of TPUs could be repurposed for blockchain functions. Ethereum could implement TPUs to accelerate complex mathematical functions, such as those required for cryptographic validation and transaction processing. C. Field Programmable Gate Arrays, FPGAs. FPGAs are highly versatile hardware components that can be configured to perform specific tasks efficiently. They are already used in various blockchain mining operations due to their ability to accelerate hash computations. By customizing FPGAs to optimize Ethereum's transaction validation and cryptographic processes, Ethereum could achieve greater throughput with minimal energy consumption. D. Application-specific integrated circuits, ASICs. ASICs are custom-built chips designed to perform a very specific task extremely well. While ASICs are typically associated with proof-of-work mining, their potential in accelerating blockchain operations extends beyond mining. Ethereum could develop specialized ASICs designed to optimize transaction processing and consensus validation, leading to more efficient scaling. Integrating these hardware solutions into Ethereum's architecture would require significant investment and technological development, but the results could be transformative, allowing the network to achieve unprecedented scalability and performance. 5. The impact on Layer 2 solutions. As Ethereum explores the potential of hardware acceleration, it's important to consider how this development might impact the existing Layer 2, L2 solutions. L2s, such as optimistic rollups and ZK rollups, were created to alleviate congestion on Ethereum's Layer 1 by processing transactions off-chain and only submitting final results to the main chain. These solutions have played a critical role in Ethereum's scalability efforts, offering faster transactions and lower fees. However, hardware acceleration could reduce the reliance on L2 solutions. If Ethereum's L1 becomes capable of handling 10,000 TPS with the help of hardware optimizations, the network could process a much larger volume of transactions directly without needing to offload them to L2s. This would lead to a more streamlined system, where Ethereum's main chain could support more users and applications without the added complexity of L2s. That said, L2s would still have an important role to play, especially in providing customized solutions for specific use cases. For instance, ZK rollups are particularly well suited for privacy-focused applications, and Layer 2s will continue to offer scalability and flexibility for DApp developers. In this sense, hardware acceleration on Ethereum's Layer 1 would not render L2s obsolete, but rather complement them, creating a more balanced and robust ecosystem. Challenges and risks. While hardware acceleration offers tremendous potential for Ethereum, there are several challenges and risks that must be addressed before it can be fully integrated. A. Decentralization and network security. One of the core principles of Ethereum is decentralization, which ensures that no single entity or small group of entities can control the network. The introduction of hardware acceleration could lead to centralization concerns, particularly if specialized hardware becomes expensive or difficult to acquire. In this case, only a small subset of participants with access to powerful hardware might dominate the network, undermining Ethereum's decentralized ethos. B. Cost and accessibility. Integrating hardware accelerators into Ethereum's architecture would require significant investment in new hardware infrastructure. The cost of upgrading nodes to support GPUs, TPUs, FPGAs, or ASICs could be prohibitive for some participants, potentially leading to a concentration of mining and validation power. This could exacerbate the wealth disparity in the Ethereum ecosystem, with only those who can afford the high upfront costs of hardware acceleration gaining access to the most efficient network performance. Compatibility with Ethereum's current design. Ethereum's existing codebase and ecosystem are not designed to support hardware acceleration out of the box. Integrating hardware optimizations would require significant changes to the network's software and infrastructure, which could introduce compatibility issues and bugs. Ensuring that the network remains secure and reliable after such changes would require rigorous testing and potentially a series of hard forks or protocol upgrades. D. Hardware dependence and obsolescence. The rapid pace of hardware development means that today's cutting-edge hardware might be obsolete within a few years. If Ethereum becomes heavily reliant on specific hardware solutions, it could face challenges in maintaining long-term scalability and performance. Additionally, new hardware breakthroughs could introduce new challenges, such as the need to constantly upgrade infrastructure or the risk of hardware shortages. 7. Conclusion. Hardware acceleration represents one of the most promising solutions for Ethereum to overcome its scalability bottlenecks and scale to 10,000 TPS. By adopting specialized hardware such as GPUs, TPUs, FPGAs, and ASICs, Ethereum can significantly improve transaction throughput, reduce latency, and optimize consensus validation. This could pave the way for Ethereum 3.0, enabling the network to support a new generation of decentralized applications and services at scale. However, the successful implementation of hardware acceleration will require careful consideration of the trade-offs between scalability, decentralization, and cost. Ethereum's transition to a highly scalable future is not without risks, and its community will need to navigate these challenges thoughtfully to ensure that it remains secure, decentralized, and inclusive. Ultimately, Ethereum's journey towards 10,000 TPS will require a balance between innovation, infrastructure, and its core values. With the right combination of hardware and software optimization, Ethereum has the potential to maintain its leadership role in the blockchain space and provide a decentralized infrastructure for the world's digital economy.